You know that we have seasonal changes, such as longer and warmer days in summer and shorter and cooler days in winter. But why do the seasons occur? We'll explore the answer in this video, which follows the cosmic context figure you'll find in your textbook. Before you continue, you may wish to review the narrated figure titled Earth's Rotation and Orbit. You should also keep two key points in mind as you think about the diagrams in this video. First, these diagrams greatly exaggerate Earth's size relative to its orbit, because Earth would be far too small to see if we showed it correctly scaled in this view. The Sun's size is also exaggerated. Second, while this perspective view may make it look like Earth's orbit is highly elliptical, in reality Earth's orbit is quite close to being a perfect circle, and Earth's minimum distance from the Sun is only about 3% less than its maximum distance. Many people incorrectly guess that the seasons are caused by the small variations in Earth's distance from the Sun, but if this were true, the whole Earth would have summer or winter at the same time. As you probably know, this is not the case. For example, when it is summer in the northern hemisphere, it is winter in the southern hemisphere. The real cause of the seasons lies with the way Earth's axis tilt causes sunlight to fall differently on Earth at different times of year. Recall that as Earth orbits the Sun each year, it also rotates daily around an axis that is tilted by 23½ degrees relative to a line perpendicular to the ecliptic plane. The axis remains pointed nearly in the direction of the North Star, Polaris, throughout the year. As a result, the orientation of the axis relative to the Sun changes over the course of each orbit. For example, the northern hemisphere is tipped toward the Sun in June and away from the Sun in December. The reverse is true for the southern hemisphere, which is tipped toward the Sun in December and away in June, which is why the two hemispheres experience opposite seasons. We can now see the key seasonal effects by zooming in on Earth, shown here in June when the northern hemisphere is oriented most directly toward the Sun. The yellow arrows indicate the direction of the incoming sunlight that is hitting Earth. Notice that noon rays of sunlight hit the ground at a steeper angle in the northern hemisphere than the southern, which is why this position represents northern hemisphere summer and southern hemisphere winter. The more direct sunlight in the northern hemisphere explains both the shorter shadows and the fact that sunlight is more concentrated, which is why it tends to be warmer in the summer. Of course, the southern hemisphere has less direct sunlight at the same time, explaining its longer shadows and cooler winter weather. Also notice that much more of the northern hemisphere than the southern hemisphere is in sunlight, which is why the summer hemisphere has longer daylight hours, with the Sun following a longer and higher path through the sky. Now consider this question. Suppose you were standing at the North Pole. As Earth rotates over a full day at this position, what would you notice about daylight and darkness? Would you have exactly 12 hours of daylight and 12 hours of darkness? Exactly 24 hours of daylight followed by nightfall? Continuous daylight or continuous darkness? The answer is C, continuous daylight. You can see why by visualizing what happens as Earth rotates at this position. Because the North Pole is tilted toward the Sun, Earth's rotation does not change the way sunlight is hitting it, which means you would see the Sun circling around your horizon all day long. You'll therefore have continuous daylight until Earth moves around its orbit to a position where the North Pole is no longer in sunlight. As we zoom back out, notice that this moment when the northern hemisphere is most directly tilted toward the Sun is called the June solstice, and it occurs around June 21st each year. We also define three other key points in the orbit. 3 months after the June solstice, we reach the time of the September equinox, around September 21st. The word equinox means equal night because we have 12 hours of daylight and 12 hours of darkness on this date. Sunlight is striking both hemispheres equally at this time, but the northern hemisphere is moving into fall, while the southern hemisphere is moving into spring. By the December solstice, which occurs around December 21st, Earth is on the opposite side of the Sun from where it was on the June solstice. If we zoom in to see the way sunlight strikes Earth at this time, you'll see that it is essentially the opposite of what we saw at the June solstice, which is why it is now winter for the northern hemisphere and summer for the southern. Our final special point is the March equinox, when sunlight again strikes both hemispheres equally, and we again have 12 hours of daylight and darkness. The difference from the September equinox is that it is now the northern hemisphere moving into spring, and the southern hemisphere moving into fall. To summarize, we have seasons because our planet's rotation axis is tilted relative to its orbit. Although Earth's orbital distance varies slightly over the course of each year, Any effects of this variation are overwhelmed by effects due to axis tilt. If Earth did not have an axis tilt, we would not have seasons. We can apply the same ideas to other planets. For example, Mars and Saturn have axis tilts similar to Earth's and therefore also have seasonal changes as they orbit the Sun. Uranus is tilted much more than Earth, which gives it much more extreme seasons. In contrast, Jupiter has very little axis tilt and therefore has no significant seasonal changes. It's also worth noting that while Earth's varying orbital distance does not affect our seasons, the same is not always true for other planets. For example, Mars has a more elliptical orbit than Earth, which puts it significantly closer to the Sun during its southern hemisphere summer than during its northern hemisphere summer. As a result, Mars's southern hemisphere has more extreme seasonal temperature changes than its northern hemisphere. As you continue your studies, you'll learn more both about seasons on Earth and seasons on other worlds.